It was a difficult task thinking about what to talk about because they stressed we should think about what could the next breakthrough in the next 5 years be. And I thought about it, and then I thought, yeah, I want to speak after the LHC talk because that's where I think we're going to have a breakthrough in the next 5 years. Oops. Well, so much for the breakthroughs. Okay. New searches for dark matter in particle collisions. I'm going to predict a very, very definite idea for what we might discover at the LHC. What we might discover is not just a new particle, but a new particle whose decay is going to tell us what the origin of dark matter was and how it was produced in the early universe. That's a pretty definite prediction, and in order to understand and for you to evaluate that prediction, you need to know where we are in what I call the cycle, the discovery cycle. It's not always true, but it's often true that discoveries in physics go through a cycle where it starts with asking questions, basic curiosity, framing how to get experimental set up to get your data. Once you've got the data, you look at the data, you look for patterns, and patterns emerge, and if you're lucky, a real theory comes out of that. And then and then on to the next cycle. So it often, but not always, but it often goes in these cycles. A critical question then is, what is the time scale for this cycle? And that depends on the sort of phenomenon that you're interested in. If you're in some very, very restricted phenomenon, it could happen pretty quickly. But if you're interested in the really big stuff, the really big cycles, you know, the time scale can be a century. It's not nice to say that, but it's true. And so I thought it would be fun to look at a half century of particle physics in the era of 27 to 77, roughly. The dates are a bit fuzzy. But the questions appeared right at the late 20s here, when we needed to understand what was the description of particles in their interactions such that they could be consistent with the recently discovered quantum mechanics and also special relativity. That was the driving thing one had to do, and it took a 50-year cycle to get there. The data poured in the 30s, 40s, 50s, 60s, every decade, all the way up to the 70s. The data was really pouring in, starting with neutrons, muons, began with particular particles, but ended with symmetries and interactions. Along the way, there were plenty of patterns emerged. Here's a pattern from the early 60s of the kaons and pions forming this hexagonal structure. It's pretty obvious there's a pattern behind there, and that pattern was what led people to introduce quarks as the constituents of all of hadrons. Theory was much harder. The first part of the theory came in the late 40s, the quantum version of electromagnetism. Here there's an electron interacting with a photon, and it was a real struggle. The 30s and the early 40s were a real struggle, and the struggle continued in the 50s and 60s, and the real theory didn't emerge until the 70s, the theory of the strong interactions and the electroweak unification. So this is the sort of pattern, and it can take half a century or so. But the key point to take away from this is that by the late 70s, there was a theory of particle physics, and it's immensely important to actually the difference between having a theory and not having a theory. So from the late 70s, we have a theory. Here's the standard model. The theory you can think of as a bunch of particles, the up, down, and electron, the familiar ones of ordinary matter. But there's 3 generations. There's a pattern for you right there that we don't understand. In fact, I don't understand the pattern of these symbols, but I have to construct my own theory for that, I think. But anyway, these particles are going along as they're traveling. They interact with these force fields. That's the photon, the Z, the W. These are the particles of the standard model, the gluons, and finally the Higgs boson of just a few years ago. And the interactions are parameterized. If you go deep down into this vertex, there's a whole bunch of quantum numbers and symmetries and 18 free parameters that have to be obtained from data. But this is what we call the standard model. The electroweak unification part of it was finally deemed to be correct in 77, and it only took 2 years for these gentlemen to win the Nobel Prize. Precisely that year, one of them, Glashow, a very bold fellow, decided that he would make predictions about the future of particle physics. And he says, we live in interesting times. We have a theory at last of strong, weak, and electromagnetic interactions. Many new accelerators are building to test our theory. So let me tell you a little bit about the predictions that he made back then in 1979. The first predictions had to do with the matter and the force fields, and this hasn't come out at all, which is a real shame, so I'll have to just tell you about what's supposed to be in here. This was the late 20th century version of what happened to the Mendeleev table in the 1860s. He came up with a Mendeleev table, and you had to discover the elements that fit in the blanks. And here, the blanks were the top quark here, and here the blanks were the W and the Z, and here the blanks are the Higgs boson. In a sense, one might say this was no big deal making these predictions, because once you knew the theory, they pretty much had to be there. That was true for the W and the Z, wasn't quite true for the Higgs, could have been something else, but you get the picture. And in fact, these particles, of course, the discovery took ages, but they came. But next we come to a bolder statement, and this is very bold given the exclamation marks and was proton decay. So what this should be is the proton decaying to a positron and a pi zero. And he made this prediction for very, very good reasons, and the experimentalists ran out and looked for it, and they've pushed the limit on the lifetime by 6 orders of magnitude, and so far, no success. So even though what looked like the best prediction for the next era, the next cycle, the beyond the standard model cycle, even the best predictions go awry. And that's what we have to expect once we're swimming without the real theory anymore. So what can we do with our theory? The good news is we can calculate stuff in particle collisions. The reasons why early on I thought that they discovered the Higgs boson even before they were willing to say they discovered it was we can compute how many events they should get, and it worked out right. So it was just very, very plausible that the discovery was there. The bad news is that we can't compute what the universe contains. And if we had a real theory, we should. We should be able to compute what the universe contains. Well, we can get the photons right. That's the big success. But when it comes to electrons and protons, we're really, really way off. We've got theories, but we just can't do it. Worse, we don't know what most of matter in the universe is. The so-called dark matter makes up most of the matter in the universe, and whatever we think about it, we know that it's not a particle of the standard model. So here are my predictions. My prediction is that the next breakthrough in particle physics will be in data. It will not be in patterns and theory. Because even though this beyond the standard model cycle has been going for nearly 40 years now, I don't think we're at the level of being to extract the next level of theory. I think we need this continual cycle of more and more data. We've had some hints. We've had dark energy. We've had neutrinos, and they're fantastic. We need more. Okay? So that's the first thing. The second thing is that I'm going to guess that the next breakthrough will tell us something about this dark matter. That I'm much, much less sure about. And this I'm going to say is that I don't think it's going to be our favorite candidate of dark matter. I think it'll be some huge, big surprise. What probabilities do I ascribe to this? Yeah, well, I really think it's going to come from data. Is it going to be dark matter? I really don't have a clue, but I think it will be. If it's dark matter, is it going to be some non-standard theory? Yeah, I think probably so. But I'm going to go further and say that in the next 5 years, there's a very specific new long-lived particle that will be discovered at the LHC, and that its decays will tell us exactly how the dark matter was made in the early universe. I really don't dare to predict the probability that this is right. Okay, so the early universe. So the early universe is a hot gas. We've got particles colliding. All the red dots here are standard model particles. Everything's in thermal equilibrium at some high temperature T. The great thing about thermal equilibrium is that it erases initial conditions, and you can hope to do a calculation at somewhat low temperatures. What is the dark matter? What is the reaction that determines the dark matter abundance? These are the key questions that we need to answer. And I'm going to talk about 2 very general mechanisms. One's called freeze-out, and probably the majority of the people in the audience know all about it, but I'm going to go through it anyway because I want to contrast it with freeze-in, which you probably don't know so much about. Freeze-out, we've had a 30-year job of trying to find direct detection of a freeze-out particle, and maybe it will. That's also a great possibility for the next 5 years, but I'm going to go for this freeze-in candidate. Okay, so freeze out. At high temperatures, the Standard Model and dark particles are scattering off each other. They're in thermal equilibrium. Below the temperature of the dark matter mass, the dark matter particles in blue annihilate away, and the dark matter abundance is determined by this cross-section. Here's a cartoon of how it goes. I'm going to give you some time sequences or temperature sequences. Here's the dark matter and the Standard Model particles in thermal equilibrium. On the vertical axis here is the ratio of the number of dark matter particles to the number of Standard Model particles. And on the horizontal axis is temperature, and we're at very high temperature. And at very high temperature, these are comparable number densities. Now, as the universe evolves, the first thing that happens is that as it's expanding, the numbers just dilute. The ratio of the number density of dark to standard stays constant. Notice the temperature's dropping. But as the temperature drops down towards the dark matter mass, we're not quite there yet, but we're nearly there. Now we go to temperatures below the dark matter mass, and the number of dark matter particles starts to precipitously drop because of this annihilation process. At some point, the dark matter particles, the blue particles, are so dilute they can't find each other, and at that point, we say you freeze out, and you get a freeze-out relic abundance. And the great thing about this is that we can compute the relic abundance in terms of that annihilation cross-section, and Beate showed a plot very similar to this one. Here's the cross-section as a function of the mass of the dark matter particle, and the direct detection searches where a galactic dark matter particle scatters off a Standard Model particle are these curves here. And here's some CMS searches, these horizontal ones from LHC. So let me go on to freeze-in. Freeze-in is exactly the opposite of what I've described for freeze-out. In freeze-in, the dark matter particles interact with Standard Model particles only very, very weakly. At high temperature, there was no dark matter particles around. There was just no dark matter at all because there's been no time for them to be produced by collisions of Standard Model particles. However, occasionally dark matter particles are produced, and they're produced because there's two new particles. Not only is there a dark matter particle, but there's a mother particle that I call M, and the dark matter particle comes from the decay of a mother particle. There could be hundreds of models for this, the same as there are 100 models for freeze-out, but I want to give you the generic mechanism. So the dark matter abundance is determined by the lifetime, that's what this weird thing means, of this mother particle decaying. So let's go through a similar sequence of temperature slides to show how the dark matter appears. At very high temperatures, we're starting off at very, very high temperatures, there is no dark matter particle. There's no blue particles there. There's mother particles and there's Standard Model particles. But as the universe evolves and the temperature drops, a few mother particles decay, and they make the dark matter particles here and here, and you see that the number density of dark matter particles is growing. It's growing in towards equilibrium. Here we go. There's dilution, but we're getting a relatively more and more dark matter particles until eventually the production of them stops. And the reason it stops is that the mother particles have all annihilated away and there's no more mother particles to decay to them. So this is a totally different generic mechanism for making dark matter in the early universe. Here's freeze out and freeze in compared as a function of temperature. The freeze out, you start with a huge abundance and it drops off. The freeze in, you start with none, and it comes in and levels off. Okay, we can't understand any of that, so we better not talk about it. So the key question is, can we measure this at the LHC? Can we actually make a mother particle and watch it decay to dark plus standard at the LHC? And if so, could we measure enough in order to be able to reconstruct what happened in the early universe? So here we make a mother particle at the LHC. It goes out through the detector. Maybe it stops in the hadron calorimeter. Maybe it lives a second. Maybe it lives a month. But eventually, it decays. We can't see the dark matter particle coming out here, but we can see the Standard Model stuff coming out here. The possibility of long-lived stop particles has been searched for. And the exciting thing is that there are limits from CMS and from Atlas that show that you can put limits on stop particles over 12 orders of magnitude in lifetime. So you've really got a very, very powerful probe for looking for long-lived new massive particles at the LHC. It's not just stop particles. It could be that the particles, instead of going all the way out here before they decay, it could be that they decay much, much more earlier on. I don't know what happened here. But they decay much earlier on and give you leptons or jets. Or they may decay right close to the interaction vertex, and you may get what are called displaced vertices. But each of these three detection mechanisms gives a lifetime or a distance, the distance lifetime between less than a centimeter all the way up to kilometers. And we can test, we can experimentally test these lifetimes. So everything that's colored here, we can actually see. So what is the prediction from freeze-in? Here's the key slide, and I've only got, I think, another one after this. Here's the key slide, which gives you the prediction for, let's suppose the mother particle weighs 300 JeV, so we can make it at LHC. Then this red curve here gives you the predicted lifetime as a function of the dark matter mass in order that it gives you the right dark matter abundance. Okay? And you can see that if the mass is a few keV, the lifetime is short, and we'll see it as a displaced vertex. If the mass of the dark matter particle is 100 GeV, it lives longer, and we'll see it as a stopped particle that lives about a month or so in the detector before it decays. But we can see all of that, okay? In this formula, which is totally unreadable, tells you how to relate how these quantities are related. But the key thing is that if you can measure the lifetime of the mother particle, the mass of the mother particle, and the missing mass, the dark matter particle, then you can compute how much dark matter there should be in the universe. And if it comes out right, you've resolved the puzzle of the origin of dark matter purely by looking at LHC physics. So I started off talking about the half-century from quantum mechanics to the Standard Model, and what a great half-century it was. We're now into the next cycle, the beyond the Standard Model cycle. We're about 40 years into it. I think that we're still at the level of framing the questions, thinking about the puzzles, and looking for new data that is going to guide us. That's not to say that we haven't made progress in theory. Of course we've made progress in theory. We've got many, many ideas over these decades that are really a tremendous progress, but we don't know how it all fits together. We don't know which theory is right. We may not even have anywhere near the right theory. So the questions. Here's some of the questions. Quantum theory of gravity. Why is the Standard Model what it is? What's the origin of mass hierarchies? What's the origin of the small numbers? Well, I've placed my bets on the contents of the universe. I think the next breakthrough is going to be, we're going to be able to figure out what the contents of the universe is. Thanks very much.